of IPH in delta connection or in a star connection. Now in line current, the value of line current is same equal to your value of phase current in a star connection type. So the IPH equals to 14.43 ampere. So ultimately your load line current becomes the 14.43 ampere. Now the power factor. Again the power factor for the delta connection or for the star connection for given impedance per phase, these are the same. So cos phi equals to R by Z. So by taking the ratio of R real value and by taking with the given value of Z, that is 10 ohm per phase, we are getting the value of 0.6 lagging. Again the active power P equals to root 3 VL IL cos phi. Now root 3 into VL is the line value which is given to you, that is 250 voltage. IL equals to 14.43, that is same equals to your IPH 14.43 ampere, and cos phi you already find out that the 0.6 lagging. So put the value of put the value of into equation of active power and solve with using the mathematical equation. You are getting that active power 3750 watt. So friends, in a star connection the value of active power is less than the value of active power in a delta connection. So whenever you are connecting the any kind of circuit in a delta connection, you are getting the more active power, then you are connecting that particular circuit with a particular all the value of the parameter. In a star connection you are getting the lesser value. So this much is preferred. And types of connections are lots of types of connections. You can connect the circuit in 4 types, like delta to delta, star to star, delta to star, or star to delta. You can connect all the value circuit in any manner. Now the next question, this is a optional question, question 5a, the comparison between the series and the parallel resonance circuit. Now this is important question which may be asked in many times, the series and parallel resonance. First of all, just go through the circuit of the series and parallel resonance. Series resonance and parallel resonance. Now resonant components are R, L and C. So by connecting them R, L and C in parallel and by applying the voltage to them V, this is called the series resonance circuit. Again it is known as the tank circuit. And same here, by connecting these components in a parallel form, you are getting that the parallel resonance circuit, such like that L and C are connected with parallel in R, and by applying the voltage V to that circuit, this is called the parallel resonance circuit. Tank circuit is also the another name is resonant circuit. So if you are asked in your exam, then find out the equation for the tank circuit or find out the equation for the resonant circuit or resonance circuit, then you have to then both the value of the name are same. Now move towards the comparison. The topics are, you have to just compare the topics such like that: circuit types, power factor, the impedance, the current, the frequency, magnification, the quality factor, the nature and the application. Now one by one we just compare the parameters. First of all, starting with the circuit type. Now circuit type for the series resonance, this is the purely resistive circuit, as well as for the parallel resonance circuit, this is also a purely resistive circuit. So whatever the component you are using, they are the purely resistive circuit. They are not a purely inductive circuit, because for the purely inductive circuit the value of that is it becomes 0. Now the next topic, that is the power factor. For the power factor, For a series resonance, you can find that it's a unity. Unity, it means this is a 1. It is same thing, the parallel resonance circuit, the power factor is also unity, or you can say that it's a 1. Value of unity is a 1. Now the next parameter which we compare, that impedance, that is Z. The impedance for the series resonance is minimum, that is Z equals to R. As we already talked that the impedance for the power for the already in a star connection is also less. And if you are using the parallel resonance circuit, then you are getting the maximum impedance, that is Z equals to L by C into R. Now L is for inductor, the inductance for the inductor, C is for the capacitance for the capacitor, R is for the resistance for the resistor. Now the current flowing through the both the resonance circuit, current flowing in a series are maximum, that is I equals to V by R. If we want to find out the value of current, then you are using the equation I equals to V by R. And in a parallel resonance circuit, the current is minimum, that is I equals to V CR by L. So the current in a series circuit is maximum, or in a parallel circuit is minimum, whereas the impedance in a series circuit is minimum and in a parallel circuit are maximum. As already as we all know that the current in a series connection circuit, the current is same, whereas in a parallel circuit the current are different. Now move towards the next parameter, that is the frequency. The equation for the frequency, that is f0 equals to 1 upon 2 pi under root LC. And the parallel circuit, if you are proving or find out for the parallel resonance circuit, then that becomes f equals to 1 by 2 pi into under root of 1 by mean square value of the 1 by LC minus R square L square. This is the typical frequency for the parallel resonance circuit, because you are connecting the L and C are in series, and that series connection with the parallel form of the resistor. Now the magnification. The magnification for the series are voltage type magnification, and for the parallel resonance circuit, this magnification is current type magnification. The quality factor, that is a Q. If you are talking about which one is a better for series resonance or parallel resonance, then you have to talking about the quality level which is given by the quality index, that is Q equals to omega 0 L by R, and the parallel resonance circuit, the quality factor is 1 by R into root L by C, under root of L by C. Now the nature of the series resonance circuit is the acceptor, which these are the two types of nature, either it can be acceptor or it can be rejector. So the nature of series is the acceptor and the nature of parallel resonance is a rejector. The application, series resonance circuits are generally preferred in a Q meter to make the Q meter, or if you are using the band pass filter, which can be easily some of the selected band can be easily passing through the circuit, then you have to use the series resonance circuit. Whereas parallel resonance circuit can be many times finding in the tune circuit, as we already know that the RLC circuit is also known as the tune circuit or tank circuit, or you have to just generating the oscillation, then in a making of the oscillator you are using the parallel resonance circuit. Or you can also find out the filter, Butterworth filter, Chebyshev filter, many type of filter can be made by the parallel resonance circuit, or oscillator, or IF, that is intermediate frequency amplifier. So all this stuff you can find out the parallel resonance circuit. The next question, the impedance of 20 plus J30 Z1, it is connected in parallel to another impedance of 30 minus J40. Z1 and Z2 are parallel impedance here. So the combination is connected to 230 voltage. So here you are preferring the parallel resonance circuit and given the supply to the 50 Hz AC. So calculate the total current flowing through the main circuit power factor of the circuit. The circuit is looks like that. The Z1 and Z2, the first impedance and second impedance are connected with each other in a parallel form and apply the 250 voltage with 50 hertz of frequency and current passing through it. So ultimately our goal is to find out the current and the power factor for that particular circuit. This is parallel resonance circuit. So first of all, our task is, whenever you are asking any example in your exam, then just find out the data given to you. So here our data are the Z1, this is 20 plus J30 ohm, Z2 the second impedance, that is 30 minus J40 ohm, voltage given to us is 230 voltage, or 230 to 240 to 250, whatever the voltage is given to you, because this is a single phase circuit, so the voltages range is either 230 between the 230 to 250 voltages, and the frequency f equals to 50 hertz. So these are the data given to us, and we have to use that data, and according to that data we have to just solve the equation. Starting with the first admittance, that is y1. Admittance is nothing but the inverse of the impedance. So y1 equals to 1 by z1. So now taking the value of z1, we are getting that y1 equals to 1 by 20 plus j30. So ultimately solving this equation 1 by 20 plus j30 by using the opposite nature of impedance, that 20 minus j30, so multiply and divide that one is equals to with the equation of y1 we are getting that 20 minus j30, and the denominator is that 20 plus j30 into 20 minus j30. It looks like a plus b into a minus b, so you are taking that a square minus b square, or a square plus b square. So using that mathematical equation we can write that y1 equals to 20 minus j30 upon 20 square a square plus b square, so 20 square plus 30 square. Now solving that, y1 equals to 20 minus j30, 20 square plus 30 square, so put the value of that, we can get that 1300. So y1 equals to, now divide the 1300 to 20 by 1300 and minus j30 by 1300. So we are getting the value of 20 by 1300, that is 0.0153 minus j30 by 1300. So you are getting that j 0.023, and remember admittance is inverse of impedance, so 1 by ohm is known as a mho. So the unit of admittance is mho. The admittance of the second impedance, that is y2, again using that equation 1 by z2, so y2 equals to 1 by 13 minus j40. So now here the opposite nature of that 13 minus j40, that is 30 plus j40. So multiply and taking the multiplication and denominator dividend of that, we are getting the y2 equals to 1 minus 13 minus j40 into 30 plus j40 upon 30 plus j40. So they are nothing but the equal to, we are putting the into 1. So y2 equals to 30 plus j40 upon 30 square plus 40 square. So just by solving that, y2 equals to 30 plus j40 upon 250, individually putting the value of 2500 into individually 13 and the j14, we are getting the value of y2 equals to 0.012 plus j 0.016 mho. So here we are getting the y1 and y2. So now by summation of y1 and y2 we are getting the net admittance, that is y. So we are getting that y equals to y1 plus y2. The net admittance of equation of y1 is 0.0153 minus j 0.023 plus y2 equals 0.012 plus j 0.016. So here how we can collect the net admittance. So here just summation of taking the first to first value like 0.053 plus 0.012, and by taking the summation net summation of j 0.023 and 0.016, we are getting the value of y, that is 0.0273. 0.0273 is the summation of 0.0153 and 0.012, and by taking the mode of 0.023 and 0.016, here what happens, the 0.016 is differentiate from the 0.023. So finally we get the value of y equals to 0.0273 minus 0.07, and by taking the under root mean square under root of 0.0273 square plus 0.07 square, we are getting that y equals to 0.0751 ho. So this is the total admittance of parallel resonant circuit. Now according to the net conductance, that there are two parameters G and B. G is the net conductance and B is the net susceptance. So 0.0273 is a G and the net susceptance, that is a B. So into this one is in the equation of y, G plus JB. So whatever the value of here is indicated as a net conductance, and whatever the value of here with the value of multiplication of J is a net susceptance, that is B. So it maybe your y equals to like 6 plus J 5. So G is your 6 and B is plus 5, or if you are write like that, y equals to 6 minus J 5, then your G is already 6, but here your B becomes minus 5. So total current, that is I equals to V into Y. Now V is given to us, that is 230 voltage, and Y, that is a net admittance. We prove that 0.075 sorry. So I equals to 230 into 0.075, we are getting that 17.273 ampere. Now the power factor, the equation for the power factor, that is cos phi equals to net conductance, that is G, upon net admittance, that is Y. So by taking the ratio of G by Y, we are getting that 0.0273 by 0.751. So cos phi, that is power factor, 0.3635, and the value of this one is below the unity. So cos phi power factor is lagging with the lagging